I hope you all can see my screen.
We have it, yes, we can see.
Okay, thank you, Mary. So before we start the topic for today, I quickly just want to uh, highlight two of the previous webinars that were relevant to today's topic. One on antenna analysis or simulations, and the other on antenna design life cycle. The recordings of both these webinars are on YouTube. So I encourage you all to watch them if you haven't attended those previous webinars. Okay. Now, coming to the outline for today's talk, we will first review the antenna design process, followed by a quick introduction to Feko. We can then look into the Feko component library and then jump into the optimization, more specifically the workflow of setting up optimization in Feko and how to analyze the optimization results. Okay. After that, we can look into the parametric sweeps, like how to set up a parametric sweep and how to analyze the parameter sweep results. Last but not least, we'll then look into the amazing free resources available on Altair Learning Center, especially for students. So there are a lot of free resources. Okay. And of course, I can definitely answer questions at the end, but please don't wait till the end to ask your questions. Unfortunately, Dr. Reddy could not join today. So instead, my colleague, Evan Urban, joined, and he is monitoring the chat. So please type in your questions as they come in the chat, and Evan will try to answer them as they come in. But if there are any questions left, I can definitely take them towards the end. With that, let's start with the typical design process of antennas. Okay? We always start with the requirements or the specifications in terms of the intended application to where the antenna will be used, or the operating frequency, the required gain, and etc. Okay? And based on the antenna design engineer's experience and the requirements, one can pick an antenna from a library if they maintain such a library, or if they are using a software like Feko, it has a component library, which is basically a database of pre-designed antennas. Okay? I will explain more about this component library later. Okay? If the antenna the need is not part of the library, then you can do some research about the suitable designs and come up with a new design. Okay? However, the initial design most likely will not straight away meet the specifications. So it would be an iterative process to fine tune the design, either manually or using built-in optimization tools like in Feko. Okay? After such an iterative process, we will then have the final antenna design that meets the desired specifications. Okay? Of course, later on, there will be like fabrication of the antenna and the measurements and all that. But I won't be talking about all that process because it's basically out of scope of this particular webinar. Okay, today we'll mostly focus on the design process limited to the analysis and optimization. As I mentioned Feko a couple of times, without spending too much time, let me quickly give you a brief overview on Feko. It is nothing but a 3D electromagnetic simulation software with multiple frequency and time domain solvers, all integrated into a single interface. Yeah. And because of such an integration, it is widely used for a broad range of applications like antenna design, antenna placement, EMC, MI, RCS, bioelectromagnetics, and so on. Okay? You can definitely learn more about the software and the applications by visiting our website, altair.com. And these are all the different solvers available in Feko. As you can see, Feko has almost all the commonly used computational electromagnetic methods or the solvers. Okay? The top three, UTD, physical optics, and RLGO, those are called the asymptotic methods. And the remaining ones are called the full wave solvers. Okay? Basically, when we say a full wave solver, the Maxwell's equations are solved exactly without any approximations. And for that reason, these full wave solvers are typically used for antenna design. Whereas the asymptotic solvers, which involve some high frequency approximations, they are suitable for electrically large structures. That is why they are typically used for applications like antenna placement. Okay. The MLFM solver, which is in between, it is a full wave solver, but the boxing algorithm is basically suitable for electrical large structures. For that reason, it is always recommended to be used with only electrical large structures when the geometry is multiple wavelengths in size. Okay. So that is all about Feko. I don't want to spend too much time on the introduction part itself. Okay. But as I mentioned during the antenna design process, if there is a library or a database of pre-built antennas, one can definitely make use of it without spending too much time in designing antenna from scratch. And when it comes to Feko, it has a library which we call the component library. Yeah? So let's look into it in more detail. Any of the pre-built antennas in the library, they can be used for quick studies instead of designing an antenna from scratch. Okay. One can pick the antennas from the library by searching for the suitable ones based on keywords related to the antenna type, like wire antennas or patch or horn, whatever the keywords you can think of. And then once you pick an antenna from the library, you can easily modify the solution settings to meet any specific design requirements. Okay? And these antennas in the library, they are fully parametric, meaning when you look at the antenna dimensions, the dimensions are controlled by variables instead of hard numbers. And because they are controlled by variables, those design variables can be used to set up optimization and fine tune the design later on if you need to readjust the design for a different frequency range or for increasing the gain or whatever the requirements might be. Okay. So let me quickly give a live demonstration of the component library before we proceed further. Okay. Well, I will open Feko first. Okay. And here on the home tab itself, you will see a component library. When you click on it, it will pop up the entire library where you can see a long list of some pre-designed antennas. Okay, let's say I search for an antenna type, for example, patch, and all the relevant ones will be shortlisted. Okay? And you can pick any design from here. For example, if I pick, let's say, truncated patch, okay? And you can see the typical performance here, and also the suitable solvers that can be used to analyze this particular design, like method of Mintz, finite method, or finite difference time domain. Okay. And if you click on next, this is where you can specify the frequency. Let's say I want to design this for 2.4 gigahertz. Okay. And I want it to be like a finite design instead of an infinite ground plane, because later on, let's say I want to fabricate this, then I definitely want to analyze the performance with a finite ground plane. So I'm going to add a ground plane. There won't be any other platform to mount, so I don't need to align it. And then if I click on create model, it will be automatically added. And if I expand the variables, you can see all the different design variables that are used to create this particular geometry. And if I expand the geometry, you can see all the different geometry parts. And if I open any of these parts, you can see that okay, the design variables are used instead of hard numbers. Yeah. And then so you can see there is a patch at the top, there is a ground plane at the bottom, and they have a feed wire extending from the ground plane to the patch. So this is a printed patch on a dielectric substrate. We can also look into the dielectric material. Okay. So if I see the epsilon r, this is 2.2, so the dielectric constant is 2.2. If I look at the frequency, so I selected a single frequency, it's a 2.4 gigahertz. I can save this model. Let's say save as okay. And if I run the solver, we can quickly look at the results as well. And if we open post Feko, we can definitely look at the results here. So if I see here, there is a request for far field. So if I add the radiation pattern, you can see this is 2.4 gigahertz. And this is the 3D radiation pattern of the patch. I can also plot it on a 2D graph, theta wrapped. And if I duplicate this, I can plot the orthogonal cut plane. So you can see the radiation pattern in the two principal cut planes. Okay. If you want, we can also plot the source data and look at the reflection coefficient or the input impedance. Okay. So all the data will be available. Okay. So this way, one can easily like pick an antenna from the library and add it to your project. And if you want to, let's say, tweak this design, you can easily just update the design variables and tweak the design. Okay. Or if the initial design is not meeting the specifications, you can then set up the optimization and define an optimization goal and then run optimization. Okay. As I mentioned, let's say if the initial design we came up is not meeting the specifications, okay, or in other words, it's not the optimal design, okay? Then obviously we have to fine tune the design, and this is where the built-in optimization in Feko comes in handy. Okay? So let's quickly look into all the different optimization methods and the workflow. And then we will once again go through a live demonstration of setting up optimization and analyzing the optimization results. Okay. And when it comes to Feko, the optimization is built into Feko, and it also supports multi-objective optimization. Okay. And Feko has several optimization methods to choose from. Okay. Some of them are global optimizers, and some of them are local optimizers. Okay. Let me try to explain the difference between local and global optimizers. Okay. When you have an optimization search space based on the range for the design variables, so you form a search space where you're trying to find the optimal solution. Okay. So in a given search space, there can be many local minima, but there will be one global minima, which is the optimal solution. And whenever you start an optimization, you obviously give a start point for every design variable. And if that start value is close to a local minima, then a local optimizer will converge to that local minima. It won't look for the global minima. Okay? But if you use a global optimization method, irrespective of the starting point, it will always look for the global minima. For that reason, the global optimizers will take more iterations to converge compared to the local optimizers. Okay. So what I recommend generally is when you start an optimization, start with a global optimizer, run it for few iterations, and then stop it. And Feko will always save the best of these iterations into a separate file. Now that you know the best of these first few iterations, give that as a starting point to a local optimizer. So hopefully, or like most of the times, the best of first few iterations would be closer to a global minima. That way, a local optimizer can converge to a global minima quickly. Okay. And of these five methods, particles form, genetic algorithm, and GRSM, those are the global optimizers. Whereas simplex and ARSM, those are the local optimizers. Okay. And when you set up optimization in Feko, you have the option to choose whichever algorithm you want to use. If you are familiar with one particular algorithm, you can go with. But if you ask me for a recommendation, I would recommend GRSM because it also has inbuilt machine learning capability where it forms a response surface and try to fit that response surface to find the optimal solution. Okay, so instead of just simply following a brute force algorithm, it has the ability to come up with like a surrogate model and try to fit that surrogate model on the optimal solution and try to achieve that optimal solution. Okay. Now, when it comes to the workflow, irrespective of which optimization method you are using, the workflow to set up optimization would be the same. Okay. Obviously, you need a parametric model. Okay. Instead of designing the geometry with hard numbers, always use design variables to control the geometry dimensions. Okay. And then you can add an optimization search. When you add an optimization search, you have the option to select the optimization method. And once you add the search, then under the optimization parameters, you need to add the design variables and then specify a range for those design variables. And that is where you also need to specify a starting point for those design variables, which typically will be within that range. And then you need to define an optimization goal to tell the optimizer what it is trying to optimize. Okay, the goal can be impedance goal to optimize the input impedance or S parameters or gain, whatever is the output quantity you are trying to optimize. You need to define a goal. Okay, and in order to define a goal, depending on which quantity you are trying to optimize, you need to have a request for that quantity in your project. Okay, using that request, you will be able to define the goal. And once you have the setup, you run opt Feko. Then once the optimization run is complete, then you go to post Feko to plot the optimization results. Okay. So let me try to demonstrate this entire workflow using an example. So instead of using this one, let me try to open a different design. Okay. So I have a slotted patch antenna. I selected this design. Instead of on a finite substrate, I'm using an infinite substrate using planar Green's functions because that way the model will run quickly. So I don't need to wait too long for the results. Okay. And this is a slotted patch where you can see a square patch and slots on all the four sides. All the different design variables used to create this particular geometry. So there is a feed underscore D, which is basically controlling the position of the feed. So you can see currently the feed is here, the pin extending from the ground plane to the patch. And there is another variable patch controlling the size of the patch. This is a square patch. And another variable to control the length of the slot, and another one to control the width of the slot, and a different variable to control the distance of the slot from the edge of this patch. Okay, and because this particular model is fully parametric with respect to all these different design variables, now if this initial design is not meeting my requirements, I can try to fine tune the design by controlling these different design variables. Okay. I designed this antenna for GPS applications. So I want this antenna to operate at 1575 megahertz. Okay. So let's say I'll try to run this over a frequency range 1.5 E9 to 1.7 E9. Okay. If I run this one, because this is a patch on an infinite substrate, it should not take too long. So that's the reason I picked it. So we should be able to quickly run it and look at the results. Okay. So you can see how fast it is running for each frequency sample. It's already done. I can open post Feko. If I look at the reflection coefficient, now you can see here, if I add a data point at 1575 megahertz, so at 1575 megahertz, the reflection coefficient is 0.6. If I look in dB, so you can say this is -4. But to make this antenna operate at 1575 megahertz, we want the reflection coefficient to be as low as possible at this particular frequency. Okay, so we need to shift the resonant frequency lower to make sure this antenna operates at 1575 megahertz. Okay. Now, if I go back to the design, this is a patch. Typically, it's not a broadband antenna. So to make sure this is resonant at 1575 megahertz, there are two ways I can set up optimization. I can either set up optimization at a single frequency, which is basically 1575 megahertz. Okay. So at this single frequency, what I will try to do is I will try to minimize the reflection coefficient as much as possible. Okay. So when this antenna operates at 1575 megahertz, obviously because of a narrow frequency range, it's not going to be operating at the other frequencies, so it will be a perfect antenna for GPS applications. The other way is if I want to look at the whole frequency range and do a frequency sweep and set up optimization with a frequency sweep. Then to make sure the antenna resonates at the desired frequency, I need to define a curve and ask the optimizer to follow that curve. And that curve should have a lowest point at the operating frequency. Okay. So let me demonstrate those two different ways. Okay. So first, let's go with a single frequency optimization. Okay. Now, once I change the frequency to 1575, I will go and add an optimization search. And this is where you can select which method you want to use. Let's say I want to use GRSM. Okay. I click on create. And once the optimization search is added, you can go to optimization parameters. So I double click. And this is where you need to add the design variables, which you can control to optimize the design. Okay. So I can add first, which is the patch length. Another one is slot length. Another one is slot width. Another one is slot to patch edge. And the last one is the position of the feed. Okay. Now, if I look at the initial value, so the start value is 22, which is the initial value. So because the start value is 22, let's say I specify a range between 22 to 20 to 24. Okay. And if I look at the slot to patch edge length, the start value is 10. So let's say we have a range from 9 to 11. Okay. And when I look at the slot width, which is 2.5, so let's say the range from 2 to 3, and for slot length, which is 45. So let's say we have a range from 40 to 50, and patch size, which is 80. That's the start point. So let's say we have a range from 70 to 90. Okay. Now, when you run optimization with this range, so the first iteration will obviously use the start value, but it will evaluate the goal function at the start value, and based on the goal function, it will start picking values between these ranges and try to achieve the goal whatever we specify. Okay. So once I add these design variables, the range and the start value, I click OK. The next step is to define the optimization goal. If I right click on the goals, I can see all the different possible goals. I want to make sure this antenna resonates at 1575 megahertz. Okay. And that output quantity is available from the source data. So I'm going to define an impedance goal to optimize the reflection coefficient, which is my S11. Okay. So I'm going to select the magnitude of S11 as my focus and say I want to minimize it. Or if you just want to minimize it, let's say you don't know exactly how much it is going to, I can also make it equal to, let's say, 0.1. Okay. So which is a pretty low value for reflection coefficient if you are looking in dB. So 0.1 is like minus 20 dB. So if an antenna has a reflection coefficient of minus 20 dB, that means it's a pretty good antenna at that particular frequency with a pretty good matching. Okay. I can click on create. Okay. So this way we can add the optimization parameters and define an optimization goal. And once this is done, we need to, instead of running Feko solver, you need to run opt Feko. But I don't want to wait too long during a live demo. So what I will do is I will go to this advanced tab. I will limit the number of runs to 5 just to show you the workflow. I'll click OK. And I'll save this model with a different name. Let's say demo _ patch. and I will click on opt Feko to run it. So you can see for the first iteration, it is picking the initial values, and for every iteration, it will create additional model files with an extension opt_1, opt_2. Okay, and you can see the values, design variables for the second iteration, and you can see a different set of model files with opt_2 extension, and this is the third iteration, all the different values for the design variables. If I go back to that folder, let me drag it here. So you can see here, okay, so now we are in the iteration 3, opt_3. There is also a separate one with an extension optimum, and this particular optimum file will be updated after every iteration. If Feko finds a better value at any particular iteration, it will automatically update this optimum file with that better values for the design variables. Okay? That way, if you start a global optimizer, run it for a few iterations, let's say 20 iterations, you can find the best of those 20 iterations under the optimum. You can give this as a start value for a local optimizer. And then the local optimizer can quickly converge to the global minima. Okay? So that is a workaround I always follow to make sure I'm not running the optimization for too many iterations and trying to get the optimal solution in a few iterations by mixing the global and local optimizers. So this is done. Let me close it. And in the same folder, you will also see a log file with the information about the iterations. And typically, if Feko has enough data to do a sensitivity analysis, you will also see that data in this log file. But if it doesn't have enough information, then that sensitivity analysis data won't be available in the log file. Okay. If I open post Feko, you can also plot the optimization data on these graphs. So I go to add results, select optimization. On the horizontal axis, you will have the optimization run numbers. We basically just ran only 5 iterations. You can see all these different design variables, the value of the design variables with respect to each iteration. But you can also look at the goal function. So the global goal, let me hide the other two. So this is the global goal with respect to each iteration. So here we are trying to minimize the reflection coefficient, right? So every time you specify a goal where you're trying to minimize, what Feko internally will do is if the output is a value that is going to be increased, then it will take the inverse of it by adding a negative sign and try to minimize it. So that way the goal function is always minimized and finding the global minimum. But if it is a quantity that is already like reducing with each iteration, in this case, the S11 is basically between 0 to 1, and we are trying to just find a lowest possible value. So here it doesn't need to take the negative and to try to minimize. So that's why if you look at the actual search goal and the global goal, they both will be same. But if the global goal is, let's say, maximizing the gain, you would see that the global goal will be like a negative value where it is going down, whereas the search goal will be the actual value of that gain at every iteration. Okay. So this is optimizing at a single frequency. Now, instead of a single frequency, let's say I want to stick with my frequency range, which is 1.5 gigahertz to 1.7 gigahertz. Okay. And I want to minimize the reflection coefficient and make sure this antenna operates at 1575 megahertz. Okay. In those cases, what you need to do is instead of specifying a goal like this as a single value, you need to define a curve. You can define a curve by using an optimization mask. Okay. So under the request tab, under the optimization group, you can add a mask. You can define a curve by specifying the values for the horizontal and the vertical axis. X will be your horizontal axis and Y will be your vertical axis. And the quantity we are trying to optimize is reflection coefficient. So X will be your frequency and Y will be the value of that reflection coefficient. Okay. So you can manually define these values, or you can also import if you have those values saved in a file. Okay. So let's say I import those values. So I have these values where I'm starting at 1.5 gigahertz. So the reflection coefficient is 1. And with every frequency, it's coming down at 1575, it's 0.1. And again, after that, it's going up. Okay. So that is how I defined my curve to make sure the lowest is at 1575 megahertz. Okay. So if I create this one, so now that I have the mask under goal, instead of a single value, I will change it to mask. Okay. So this way, the optimizer will try to follow that mask, modify our design in order to make the reflection coefficient similar to what we have as a mask. So I ran these two cases with, of course, a much finer frequency increment than what you have here, so that when I'm plotting the results in post Feko, you can see a smooth curve, and I have the results here. So you can see the red curve is the initial design, where the reflection coefficient at 1575 is only like 0.3. But by optimizing it a single frequency, which is 1575 megahertz, and making sure it has the lowest reflection coefficient at that frequency, I'm able to optimize it, and you can see the reflection coefficient, which is the blue curve. Now, by running a frequency sweep and using an optimization mask, I ran again the optimization, and you can see once again we are able to minimize the reflection coefficient at 1575 megahertz, and you can see the same response. Okay. So you have two options. Either you can pick a single frequency, or you can do frequency sweeps. But depending on the final result or what are your requirements, what you're trying to achieve, you can either go with an optimization mask to define a curve, or you can just simply specify single values. Hope that is clear. Now that we learned about the optimization in Feko, now let's look into the parameter sweeps. Whenever you are trying to understand the behavior of a design, in our previous antenna case, there are like 5 design variables controlling the antenna design, right? Now, if you want to understand, okay, how each of those design variables are affecting the antenna performance, then you can simply do parameter sweeps with respect to each design variable and plot the output response against that particular design variable, okay, to see how a particular design variable is affecting the output response. Okay? And to make it easy to do the parameter sweeps, we have macro built into Feko for parameter sweep. Basically, like the API in Feko is based on Lua scripting, and it is integrated into Feko to automate any of the pre or post processing steps. Okay? And we already have some pre-built macros to make it easy for certain applications. And one of those macros is for parametric sweep. If you don't want to use the macro, you can set up parametric sweep through optimization also. If I go back, so under optimization, the grid search that you see under optimization methods, that is what can be used for parametric sweeps. Okay, so when you use grid search, And when you add an optimization variable, so here you not only specify a start value, but you also specify the grid points. Based on the number of grid points, you will have this entire range split into equal number of samples, equally spaced samples, depending on the number of grid points. And it will be basically running the model at every one of those samples. Yeah. It's not going to be any optimization at all. It will be just running the model at the specified grid points, like a parametric sweep. But instead of going through this process of setting up optimization and adding the parametric variables and adding a dummy goal in order to run OptFeco, what we did is we made it easy by making the macro available for you. Okay. So let me save this model with a different name, demo underscore metric. Okay, so I will delete this mask as well as delete the search. Now, if I want to basically run parametric sweep with respect to any of these design variables, all I need to do is go here, run this macro, and select the design variable. For example, let's say slot length. And let's say I want to sweep this from 40 to 50. And let's say I have 11 samples. Okay. Now, just to make sure we don't spend too much time waiting for the results, let's say I will limit this to 3 samples. Okay. I'll click on next. And then automatically what the macro will do is in the background, it will create separate model files for each of those 3 values, and it will run those 3 model files one after the other automatically. And at the end, it will ask a question whether do you want to combine the results from all these different iterations so that you can plot the output response against the design variable. Okay. So if I click on finish, I also selected the option run Feko solver, right? So if I click on finish, so it will launch a command prompt, and this is where it will sequentially execute all those 3 model files. So if I go back, so this is the directory where it created those 3 files, and it will automatically execute a batch script to run all these 3 files sequentially. What I will do is I will simply stop it here. So I want to terminate this one. Yes. I have from a previous simulation, I stopped once I am done with all the iterations where I can show you the question. Okay. So launch post Feko and merge the results. So this is a question that you will be asked. And to say yes, you simply hit Y. So once you hit Y, it will pop up a Lua script where you can see the folder where the results are saved. And the post Feko session will be opened where all the results are merged. Okay, so we have the voltage source sweep, right? So if I add a graph, if I simply drag this sweep, so you can see on the horizontal axis, we have the slot length varying from 40 to 50. And the vertical axis is our output response, which is the reflection coefficient. Okay. So you can see how the reflection coefficient is changing with respect to the design variable slot length. Okay. So you can do the same thing with any of the other design variable. In fact, you don't need to do it one at a time. You can also do combinations. You can select multiple variables when you run that macro and run all the sweeps at once. Okay. So through the application macro parameter sweep, you can always run parametric sweeps to gain some insights into how a particular design behaves with respect to any of the design parameters controlling that particular design. Okay. So far, we learned how to set up optimization in Feko, all the different optimization methods, how you can use optimization mask, how to do parametric sweeps. Okay. Now, before we close out, I want to point out that for students, the software is available for free. So if you go to altair.com and look for Altair Student Edition, we have the free student edition for all the Altair software, including Feko, which is under the electromagnetics domain. Okay. You simply need to create an account using your edu email. And once you create an account, you will have instructions how you can download the software, how you can install it, how you can get a free license. So it's a fully functional version of Feko without any limitations. So you can definitely use it for your research projects. And if you are new to learning Feko, on learn.altair.com, there are a lot of videos that can be used for learning the software. These courses, embedded courses, these are pre-recorded training courses. Okay? But apart from the pre-recorded training courses, there are also live virtual trainings. So you can register for any of these trainings, once again for free of cost, and you can attend them live, where my colleagues, one of them will be doing these trainings live. Okay, so in a live training, you get a chance to do some live hands-on exercises and ask questions to the instructor and get clarifications. Okay, so you have two options to learn, either through the recorded trainings or through the live trainings. Okay. Last but not least, I also want to highlight this book, which is co-authored by Dr. Reddy. So this is an antenna book. It's not a Feko book, but the exercises in this book, they are done using Feko.